Hi, my name is Russell Fox, and I'm a student at the University of North Carolina, Charlotte. And I will be presenting today a dryer test set. The dryer test set measures 4 sensors, and those 4 sensors are a current transformer, which tells how much current that the whole dryer is using, and the other 3 sensors are a relative humidity probe, which tells the percentage of relative humidity of the exhaust of the dryer, along with a temperature sensor that's in the exhaust also, and a wind speed sensor that'll tell you in meters per second how fast the air is flowing through there. The temperatures is in degrees Celsius is the units, and the relative humidity is percent. Current is in amps. So if you could come around here and I'll explain to you what we got going on here. The test system's comprised of a PC that has a virtual instrument that was designed in a LabVIEW platform, and the USB 6008 is a National Instruments data acquisitions card, so it's connected to your PC. This data acquisitions card is monitoring those 4 sensors, and the current sensor right here is connected to channel 1, which is AI0. The first channel is AI0. Has a resistor right here, a power resistor, and it's connected to, if you come around back here, this current transformer right here. We took one of the hot legs of the 240 coming into the dryer to put the current transformer on. Now the next channel that we'll talk about is AI1 and AI3 or AI2 actually go to a temperature probe. The temperature probe is put into the exhaust right here, this stainless steel probe, and this black probe here is the wind speed probe. Now the probes, the relative humidity and temperature is in the same probe. It's an omega probe, and what it does is it gives a current in a range of 4 to 20 milliamps. So what we do there, so full scale, 4 to 20 milliamps for relative humidity is 0 to 100% relative humidity, and 4 milliamps to 20 milliamps is 0 to 100 degrees C full scale. So what we have in the data acquisitions card is it can't measure current. So I put a 2 resistors, they were 250 ohm, but they measured like 267, and that current drops across the resistor and produces a voltage for which the data acquisitions card can monitor. Within the program, we calibrate to be able to equate that voltage to whatever the respective relative humidity and temperature is. Now the airspeed sensor, the black probe that I showed you earlier, is actually just a voltage, which is 0 to 10 volts, and that gives you a 0 to 20 meters per second full scale. So there's no resistor needed there. So that's how our instrumentation's hooked up to the dryer, and I guess now, since you understand the system, we'll show you how it runs. Okay, I'll shut my dryer door here. Guess you can come over here. take a look at the front panel. So this is what we have in LabVIEW right here. This is all of the sensors. I'll make sure that they're all turned on. This is the log time. What the log time does is allows the user to set the amount of time that it logs data and dumps it to a CSV file, a comma separated variable file. And here we have controls, and the controls comprised of a start button and a stop button. Start button starts your test, stop button stops your test. This measurements labeled graph here is a graphical representation of all of your 4 sensors, real time. Green, or here's a legend right here. White is for current, red is for temperature, green is for relative humidity, airflow is blue. Here you have your indicators, and these indicators are just a numerical representation of your 4 sensors. So you can look at the graph, they're being graphed real time. You can also look at your indicators, because the indicators are being populated real time with the numeric values. Then what you have here is a start time and date. That actually tells you when you first started the test, which is useful, you know, if you just so you know what time you started. If you started it and then walked away and you were curious to know how long it was into that cycle, the time would let you know. This elapsed log time, what it does is tells you, is like a counter for the next log. So if you set this to 6 seconds, this log time would count up to 6 seconds and then pull all of the values that are in these numeric indicators and dump them to the CSV file. So you're acquiring data with a timestamp. It also records a timestamp for each measurement, so you know at what time in the cycle you got those readings. So let me go ahead and start it up so you'll see. I'll go ahead and start this VI by pressing run, and then I will select start here. Well, actually, yeah, we'll leave that 6 seconds. I'll hit start. Now it'll ask me where I want to save the file to. The default is the desktop, just so I know where the file's at. So we'll name this file test. And then we hit OK. And right now we are running. If you notice, the relative humidity's 40%. It's pretty hot in here because I've been running this dryer without the exhaust on it. That's just the easier way to access it, to take the ductwork off the back there. So what we'll do now, if you notice, the current is, you know, 27 milli, so it's nothing pretty much. Temperatures right now, like I said, it's hot in here, so it's about 32 C. Relative humidity is around 40%, and the airflow is nothing because it's not running. So what we'll do, door shut, turn on our dryer. If you noticed, our current has went up to 16.8 amps RMS. Temperature is about 35.8 C, it's climbing 36. The relative humidity is pretty much the same because the clothes are dry that are in there actually. If the clothes were wet, this would be a much larger number. And the airflow is at 11.68 meters per second. And here we have our start time and date, and this is a counter. If you notice, it's counting up Should count to 6 and then restart. Count to 6 and then restart. And that again is dependent on this control. We have it set to 6 seconds. Again, all our sensors are on. Stop button, start button. We're graphing real time, and these numbers are being populated real time. So that's the extent of how the test runs. I'm going to stop our dryer, which is done by opening this door. And you see everything coming back down, of course, except for the relative humidity, because it is hot in this house. Again. So I'm going to go ahead and stop. So we stop the program. Now, to give you a little bit of background, what we're doing here is we're collecting these parameters of relative humidity, temperature, air speed, and current, because what we're trying to accomplish is a more efficient dryer without having to buy a new dryer, trying to make this dryer more efficient. All this dryer knows is a time that you set and you press go, and then it continuously just dries clothes. Well, depending on the load that you put in there of clothes and how saturated they are, and just a lot of different variables there, it could be more contingent on what the load is than a time factor. So if we're measuring relative humidity, and I'm guessing just relative humidity, because if the relative humidity comes back down to X amount, the clothes are probably dry. Because if the air's not humid anymore, then that pretty much tells you that the clothes are dry. So what we got to do is we've developed this test system, do some testing with some different test cases and scenarios, use that data, and come up with a way to turn your dryer off when your clothes are dry. So that's the purpose of this project. This is the dryer test set. My name is Russell Fox, University of North Carolina, Charlotte, and signing out.